All right, so today, let's look at Earth right here. Perfect representation of it. I know this because I wrote Earth on top. Earth has a mass of 5.972 times 10 to the 24th kilograms. Essentially, it's 6 with 24 zeros after it in kilograms. That's pretty big. Nah, pretty close to Earth. We have the Moon. It has a mass of 7.348 times 10 to the 22nd kilograms. That's also pretty big. This is way bigger than anything we've worked with so far this year. The distance from the Earth to the Moon, on average, about 384,400 kilometers. There are times in the Moon's orbit where it does get closer, and there's times when it gets farther away. On average, 384,400 kilometers. There is a force that exists between these two. We know this because the Moon continues to stay around the Earth. It doesn't just fly off on its own. So that tells us that there's some force pulling on the Moon. We can see that with the fluids on Earth as well, the oceans, our atmosphere, stuff like that. The Moon is exerting a force on the Earth as well because it pulls the liquids closer to it. That's what causes the tides. We can actually calculate how much force exists between these two. Back in the day, I believe it was Sir Isaac Newton, he discovered that, or theorized that the force between two distant objects was inversely proportional to the distance between the two objects. So what he said was that the farther away two objects are, the more force we would see between them. So, and it wasn't until later that another researcher discovered out how exactly to calculate this. What they found is that the force, I'm going to put a big G there just so that we know we're talking about like cosmic gravity, not just acceleration due to gravity on Earth. All right, is equal to big G. Um, big G is the gravitational constant. It has a value that we're going to go to here in a little bit, but it's that times the mass of the first object times the mass of the second object divided by the distance between them squared. That means the farther apart they are, it doesn't just decrease according to the distance between them. It decreases by the distance between them squared. So, using this formula, and then also they've determined, scientifically that gravitational constant, it's always 6.67 times 10 to the negative 11th meters cubed over kilograms seconds. Okay. So, this is always true. Like this number, you can either memorize it or you can write it down on your note card. Either way, this is what our G will always be. You could convert this into like kilometers or kilogram or into grams. I would say you're probably better off taking your units that you get and converting them to match this constant because they all have to be the same. All right, so with this information, let's go ahead and start plugging in numbers. All right, so f of g. We'll pretend that's a g by redoing it. All right, big G, 6.67 times 10 to the negative 11th meters cubed per kilogram second. big G, mass 1. We're going to say Earth's number 1. Number 1, number 1. All right. 5.972 times 10 to the 24th times this guy here, 7.348 times 10 to the 22nd. All right. That's all over this distance squared. All right. Now, a little bit of trickiness here. Kilometers in our distance, meters in our constant. So we need to get this into meters. Let me go ahead. Kind of erase this guy here. Okay. Let's just tack on 3 more zeros and voila. I just very complicatedly went from kilometers to meters. All right. The big thing though, I need to square that. So let me actually write that in scientific notation. We went 1, 2, 3, 4, 5, 6, 7, 8. So that's 10 to the 8th. Okay. And we're squaring that whole number. All right. So this will be fun. Where do I want to start? Well, let's start with, oh wait, I need to get meters in there. And that's kilograms. I did bad physics here. Kilograms. Okay. Kilograms down here. Cancels out kilograms here. Seconds here. All right, we're going to leave seconds there. I have meters cubed here. I'm going to end up with meters squared here. So those will cancel out at least two of them. All right. Let's go through and figure this out now. I'm going to bring up my calculator. Oh, let's see how well I do with this. Okay. Parentheses. 6.67 times 10 raised to the 11 negative, closing parentheses. Good so far. Times, opening parentheses, 5.972 times 10 raised to the 24th, closing parentheses, times, opening parentheses, 7.348 times 10 raised to the 22nd, closing parentheses. All right. Dividing it, rather than trusting my calculator to do it right, I'm just going to divide it by this number twice because that should be the same thing. Opening parentheses. 3.844 times 10 to the 8th, closing parentheses, divided by, open parentheses, 3.844 times 10 raised to the 8th, closing parentheses, equals, that is a pretty big number. Let me go. Oh, disappeared on me. We got 1 point. I'm going to bring it off to the side here. We got 1.98 times 10. Bring it back over to count. We're going to go 3, 6, 9, 12, 15, 18, 20 times 10 to the 20th. And I'm going to go ahead and assume, oh, I messed up. That should be squared. So the units I end up with is kilograms, meters per second squared, which looks familiar because that's what a Newton is, okay? That seems really, really, really big, okay? So let's actually double check it. I'm just going to Google real quick, force of gravity between Earth and Moon. And it's possible that I used some wrong numbers because I used the wrong distance, didn't I? That's not giving me an answer. The distance between the Earth and the Moon I looked up is probably surface to surface. The distance I should have used is between the centers of these two things. So I should have looked for that. So that's one mistake I should have made. That's one thing you always got to make sure you're looking for. Um, it looks like I'm not off by too much. So if I bring Yahoo Answers over, put that there, okay. They use 6.672 times 10 to the negative 11th. They use 5.97, 10 to the fourth. Mass are the same. The distance they use, 363,000 kilometers. So their distance was actually even a little bit smaller. So they were dividing by a little bit smaller number here. And so they would have gotten a bigger number. But they got 1.78 times 10 to the 22nd, or 2.22 times 10 to the 20th. That's not bad. You know, we got really, really close. We got in between those two numbers. We got the average. We got the right answer. So let's just go ahead. Let's put a box around that. That's how much force there is between the Earth and the Moon. That's how much force there is that the Earth is pulling on the Moon and vice versa as well. So then the question might be, well, why doesn't the Earth revolve around the Moon? Well, the answer to that would be we have more mass. We have far more inertia. It is way harder for the Moon to move the Earth than it is for the Earth to move the Moon. But that's gravitational constant. So really, we have two things that we need to add to our note card. We got the gravitational constant equation, and then the value for what gravitational constant is. Anyway, I hope that helps out. Otherwise, good luck with the practice.